Hello and welcome to today's webinar, Process Maturity and Agility for Quantum Readiness and More. This is our mostly monthly webinar focused on all things identity and access management, brought to you by InCommon and Internet 2. I'm Jody Tracy, Program Manager for Cohorts and Accelerator Initiatives for the InCommon Academy, and I'll be your host for today. Just a few notes about logistics for today's program. Gabor, if you can, thank you. We'll be taking questions at the end of the presentation using the Zoom Q&A function. So you can find that button at the bottom of your Zoom window. So any questions you have throughout the webinar, you can submit through there. And also, again, just you're welcome to keep the conversation going in chat as well. As you leave today's webinar, you'll be asked a couple of questions. We love getting your feedback, so we invite you to take a few moments at the end of the session to do that. And finally, this event is being recorded and will become available later. So if you registered for this IAM online, you'll receive an email with a link to the recording as well as the slides. And these materials will also be posted to the InCommon website, and as always on the IAM online YouTube channel. So watch your inbox for all of those links. All right, now I will go ahead and kick it off. Again, welcome to today's presentation, Process Maturity and Agility for Quantum Readiness and More. We're here today for a conversation with Gabor Esses and Rob Carter, who are members of the Cryptographic Evolution Working Group. So I will go ahead and turn things over to our moderator for this session, Grady Bailey, Senior IAM Architect at Internet 2. Take it away.
Morning, everyone. I don't want to take up too much time because I know we have quite a bit of content to get through, because this is not a simple topic, as might be evident by anything you've heard around the conversation around cryptographic agility, post-quantum readiness, and there are a lot of complexities. We're hoping to bring those to you today, and then help make you realize the sky is not falling, at least not immediately, and we can be prepared together. There are lots of people working on all the problems that face us, both as technologists and identity practitioners, and everywhere in between, as we prepare for a potential post-quantum future. But I will go ahead and let Gabor and Rob please introduce yourselves, and then we can dive right in.
Thank you, Grady. I know you're traveling, and I appreciate you jumping on. So hi, folks. My name is Gabor Esses, and my day job, I am an IAM architect, but I'm also co-chair of the Cryptographic Evolution Working Group, which you'll be hearing more about in this presentation. And Rob?
Yeah, so I'm Rob Carter. I'm a middleware architect at Duke University. I'm also sitting on the Cryptographic Evolution Working Group, and this year vice chairing the cacti group that spawned the Cryptographic Evolution Working Group. So sort of a lot of connections to that.
So we have a couple objectives for this talk, and I wanted to talk very clearly about these, right? This is clearly a complex topic. There are a lot of moving parts, and the problem is far from simple, and lots of different parties will have to do their pieces to make progress. So one of the things we'd like to do with this talk is separate the fact from the fiction. There is as with any big conversation, it's natural to be concerned, and it's natural to be a bit alarmed. But in fact, this problem is tractable, even if large. So we want to separate that fact from the fiction and position you so to be able to understand this subject matter, and to keep an open and inquiring mind to be willing to close those knowledge gaps as you learn more about this. We also want to prepare you for this transition. This is going to be a transition that will have to take place. There will be some amount of work involved, And the way you navigate that transition is through some tried and true steps that you may recognize from some of your other ventures by cataloging an inventory, sequencing that work, and delegating where appropriate. And we also want to position you so that you can help others navigate this problem also. We are a community. That's what makes us strong. We are sitting in a room right now talking about this topic, and there will be much more opportunities in the future to have similar advocacy and similar collaboration. So we want to position you and empower you to be able to do those activities in the future. So this topic goes a long way back. Frankly, ever since we've had computers, computers are tremendously powerful devices that frankly have transformed our lives. Ever since computers took up the size of the room, now they no longer. We carry computers everywhere. And computers, of course, achieve this by layering on a bunch of different abstractions. You have designers working on user interfaces that are much easier to use than loading punch cards into a computer. You have folks that are versed in business administration, system design, layering these things together. And inside of computer is a lot of clever electrical engineering work making those calculations happen. All of this is underpinned by some fundamental theory about mathematics and ways of communicating information in the physical realm that we inhabit. And more about the weirdness of that physical realm will follow in this talk. And of course, in frankly just a couple decades, our world has been completely transformed. Everything is digital now. It is our economies, our business, government, education, entertainment, commerce. And those use cases are made possible once you take computers out of the hands of a single person behind a locked door and make them play nicely in a larger world together. You are likely going to need these properties. You will need confidentiality so you can hide information from those parties who should not be privy to the details of the information. You also want authentication to make sure that information that is received can be traced back to a specific sender. And similarly, you will want integrity to make sure that that information has not been tampered in transit. Some of these properties combine really nicely together, and many deployments of business systems and use cases are actually a combination of these things. For example, TLS, which makes possible the fact of interacting with your bank through a website, for example. TLS is a protocol that combines all three of these properties in one package. You might be wondering what this "you are here" sign is. Well, I posit that our entire industry, our trust and identity industry, essentially lies at the combination of authentication and integrity. Our position descriptions, frankly, were developed once these properties became important to implement in the digital realm using computers. And our industry specializes in achieving these things using technological tools. So if you're wondering why this topic is relevant to you at all, well, the fundamentals of our industry arise from being able to tell one subject apart from the other and ensuring that assertions of such a sort cannot be spoofed, cannot be misdirected to other parties, and cannot be tampered with. All of these underpin our identity and access management function, and they enable our trust and identity federation. So these are about as fundamental to everything that we do as you can have it. Of course, we will not be tackling this problem alone. We will be relying on experts in other fields like mathematics and cryptography, and also folks across the business to implement the specific ways that we have to achieve these properties. So, one of the ways that these properties are achieved using cryptography. And let's review these one by one. So confidentiality is information concealment. It's when you need to prevent someone from, someone not authorized from reading the information, except the someone not authorized is actually very hard to define. What this achieves is folks who are not in possession of the key or do not know the transformation, those folks will be locked away from, those folks will be prevented from interpreting the output. Um, what a cipher does, which you may have heard, you may be familiar with AES or older systems like DES or IDEA, those ciphers. What they do is they're a mathematical permutation that's reversible, and the key is the one that selects one particular permutation out of all the possible ones. So using that key, you unlock the lock that is the cipher. With symmetric encryption, which is one where all parties use the same key, and this is a picture of the Enigma machine, by the way, you run into a very difficult situation, which is that you have to exchange the keys, and we'll cover this more later. But you may have heard that there are different kinds of ciphers. There are stream ciphers and block ciphers. A stream cipher is essentially an abstraction of a one-time pad that generates a key stream using some sort of seed. And that way you don't have to distribute the entire one-time pad, which is super secure, but quite difficult to use. You only have to distribute a small key, and the rest of the one-time pad, as it were, is generated from the key. And you also have block ciphers, which are operating off of the fixed block. Of course, very rarely is it the case that all of the messages that we send all have the same length. This largely does not happen. So what we actually do in practice is we make stream ciphers out of block ciphers. You may have heard of these referred to as modes of operation. Key distribution is a big problem. This is a picture of a German key for the Enigma machine, a key schedule. Key distribution is difficult. Back in the day, you had to physically distribute this, and actually, the text in German says, "Warning: burn if it, destroy. This must not fall into enemy hands. Destroy if it does." You have to protect those keys. You have to protect the key material and everything used to generate the keys, because you don't want that to fall into the hands of parties that you didn't intend. This reliance on a single key also enables a couple different attacks, such as one you may have heard of, which is the harvest now, decrypt later, or store now, decrypt later. There are theories that this is actually taking place by many nation states. There's certainly computing power and storage power available to do this, where you operate large data centers and simply capture as much information as you can, only to hope that eventually cryptography will be continuously broken and you will gain access to those state secrets later. So frankly, that has to be part of our threat model. So to overcome the reliance on the single key, some clever folks in the 70s figured out that there are certain mathematical problems that are hard to invert. One of these is the discrete logarithm problem, and you may have heard of the Diffie-Hellman crypto system. This is commonly used for key agreement, where the two parties start off with a private key and a public key, which are different numbers. And they use a mathematical problem based on logarithms to derive a shared secret. Each party does the computation on their side, and they arrive at the same value. This enabled, for the first time, not having to exchange the actual key on the wire. And what happens instead is the two parties will calculate the same answer, and that answer becomes the key. This key can be used then for really any kind of other cipher. You can use AES. You can use bring your own cipher to make this happen. Also in the 70s, some professors at MIT figured out that you can use a problem based on integer factorization, which is similarly hard to invert, to develop a full-fledged crypto system. And this became RSA. That company went on to be a very large player in the industry. And RSA and the problem of integer factorization underpins a lot of our cryptographic output today. This is based off of the same ideas as Diffie-Hellman, except it uses a different problem underneath, a different mathematical problem, and it is a fully fledged crypto system. Now, in practice, this if you want to use this out of the box, you get some large key sizes, and it's not very practical. So what folks often do is they combine asymmetric encryption to arrive at a key, just like with classic Diffie-Hellman, and then you use symmetric encryption using that agreed upon key to do the rest of the encryption. So far, we haven't talked about one of the other things on the slide I shared earlier, which is authentication. And this is very important to our work and fundamental to a lot of things that happen with computing today. This allows us to tell one party apart from the other, where essentially their private key becomes some facet of their identity. And we assume that possession of the private key is a very good indicator of someone's identity. Now, that someone may not be a natural person. It may be a device held by the person, or it may be a agent or some other bit of computing mechanism operating on behalf of the user. But fundamentally, these underpin most of our industry today, including our jobs. A very difficult unsolved problem when it comes to digital signatures is these artifacts often need to be very long-lived. If you're doing code signing, or if you're using this to identify a user, or let's say check if somebody's passport is valid, those artifacts, including the public key, the private key, as well as the artifact that is signed by these things, the signature, those things have to live for a while. And if they expire ahead of time, which you may be familiar from TLS certificates, which is really just the same concept, then it can be difficult to reissue those things, and you have to maintain a continuous relationship to be able to reissue those artifacts. So let's overview. Yeah, go ahead.
Gabor, I was just gonna say, for everyone's benefit, we have now essentially reached the current state, right? We've recapped where we are today, and so much of our computing and everything is based on mathematics that we have used for a very long time, and they've been useful up until now. Rob, I want to give you a second to, if you want to chime in at all before we get into the dangerous future that we're about to explain.
Sure. Yeah. I mean, as Grady notes, we've basically been using this technology now for about 50 years, if you kind of work it out, right? 70s to mid 20s, that's 50 years. How many things have we been using for 50 years without really substantially changing them in this industry? Not very many, right? And it may seem like a lot of this stuff is kind of arcane because, well, frankly, it's pretty arcane, but it is very germane. Just as Gabor pointed out earlier, all of our authentication, all of our trust, really, in different parts of our sort of identity and access management landscape, depends on assumptions about certain things being true. And most of those assumptions depend on the cryptography that gets used underneath all the covers there being solid, right? We assume that if we send our password to a website while we're logging in, so we send our password to an IDP to authenticate ourselves, it's not going to be seen by anybody else because it's going over a well-encrypted tunnel. And we're using, RSA, DSA, ECC, whatever. We're using these 50-year-old mechanisms, or sometimes 40 or 30-year-old mechanisms, but they're still pretty old, to secure those connections and ensure that all that stuff stays private or stays confidential. The signatures that we use on our assertions from shibboleth IDPs or other SAML IDPs, the signatures that are involved in doing OIDC, all of this stuff depends critically on the security and sort of patency of this 50-year-old cryptography that we've been doing. And as I think Gabor is about to get into, there's now this sort of new, completely different threat that means that maybe the 50-year-old stuff isn't going to be solid forever anymore. We had a good run for 50 years, and now we maybe have to change some things. So,
Yeah, that's right. So our let's talk about this quantum threat. So our universe is built out of these funny things, not qubits, not the things you see on the screen, but they're built out of some very complex systems, which are frankly a bit headache-inducing. But smart people have figured out that you can use the properties of simply the universe around us to empower your calculations and use statistics and in some cases the impossibility of certain things to happen when you're already aware that a prior thing didn't happen, to deduce information, right, and to do calculations. So just as with a classical computer, models information using the abstract idea of a bit, which in reality is probably a very analog value that snaps between a minimum and a maximum, and all the intervening states are not relevant for the properties of the calculation. A qubit is an abstraction of a quantum system, in this case, a two-state quantum system. We'll get into states a little bit later. But a two-level quantum system, which can effectively represent a 0 or a 1. Except there's a strange complication, because in fact, the state space of this is much larger. The state space is actually exponentially larger than that of a bit. You can probably make this a little bit less headache inducing by a graphical analogy. And this is an analogy that even quantum scientists use because it works really well. You can think of the quantum space of a qubit, or you can think of the state space of a qubit as being on the surface of a sphere. And it's shown here using that Greek psi sign. And it can't, it can be more than just 0 or 1. It can also be anywhere on the surface of the sphere. And the true value is possible to measure, but if you measure, you actually get back a 0 or a 1. You don't get back the real value. You get back a 0 or a 1, but you get back that result with a probability of that depends on that internal state. And you can use these properties in some quantum algorithms to to deduce certain states that would have been impossible given given your access to that prior information. So quantum algorithms are ways of doing calculation using quantum systems. And just like with normal computers, you can build gates. In the case of quantum algorithms, these will have to be reversible operations that transform essentially the inner state of that sphere that was shown to you earlier. And you can think of these as matrix operations, and in fact, some of the algorithms are devised using matrix operations that essentially rotate the state space of the qubit underneath. You can arrange these gates into circuits. The combination of applying, multiple gates, mathematically that's called the tensor product. You can sort of think of that as when you're stacking matrix multiplications together. And in any such circuit, you will probably want to do your measuring at the end because, as we said earlier, once you measure the quantum state, it collapses. What that means is every successive time you measure it, you will get back the same answer. You can use that property to then reduce down your the probability of the values that you know can't happen. So in some, you can stack these techniques together to have some pretty clever algorithms. You can pack and unpack from the phase, which is one of those angles that you saw in the drawing here. This is the phase. You can pack and unpack values into there and essentially use it as free storage. It's really neat. You may have heard about Fourier transforms from signal processing. Well, it turns out that there is a mathematical analog to the Fourier transform called the quantum Fourier transform. That operates on it. And just as Fourier transform is used to make, let's say, JPEG compression possible, or MP3s, and compress down the information, it's sort of a similar technique where you can use it to pack information into qubits. And in any sort of quantum computing, you generally are trying to get your statistical probabilities to amplify the likelihood of the so-called good answers, and use essentially destructive interference to cancel out all the bad answers. I understand this is a bit headache inducing. Frankly, it is for me also. There are folks who specialize in this kind of stuff. And it's okay that we're not experts in this. We're always going to be reliant on experts in particular problem domains, just like with this one. But it is important to understand where exactly the quantum advantage comes from. And in pop science, it's sometimes described that quantum computers can do many calculations in parallel, and that's not strictly true. That's not really what's happening. Instead, what's happening is you're manipulating a bunch of matrices and you're rotating this internal state, and by measuring things, you can sort of rule out outcomes that couldn't have happened, and you can use that to arrive at the good answer. So in 1994, a graduate student for MIT, who later became a professor, Peter Shor, he had been reading about quantum algorithms, and he had developed Shor's algorithm. And this is the algorithm that threatens the asymmetric crypto systems like RSA, like Diffie-Hellman. This is a clever technique to perform a class of problem of which these two problems are a subset on a quantum computer, using a combination of these techniques that were discussed in the previous slide, the phase estimation and the quantum Fourier transform. And it gives a pretty significant speed up because it reduces the problem from abstract exponential time to polynomial time. There are a couple caveats with that. The speedup is obviously not free. We'll cover that in a later slide. 2 years later, a gentleman named Grover came up with a different kind of algorithm that actually uses many of the same techniques underneath to speed up cases where you're able to use the amplitude amplification discussed in the previous slide to start canceling, to basically separate the problem into two states of the good answers versus the bad answers, and use the destructive interference to start canceling out all the bad answers. And what this ends up doing is it causes a quadratic speedup, which is a square root factor of n over everything else. So practically what this does is, if you've got a 128-bit AES key, then with a quantum computer, you can basically treat it as a 64-bit AES key. So that's a pretty significant threat. Once again, there's a couple caveats with the Grover's algorithm in that even though it's a theoretical quadratic speedup, not all that speed can be realized for real, and we'll get to that later. Using this excellent paper, What is Quantum Parallelism Anyway? I am including a couple pictures here that actually explain what's happening. I have, I'm putting together this presentation. I've searched and searched and searched. of useful mnemonics and useful thought models to figure out what's really happening inside of quantum algorithms. And after much rumination, this is the best material I could find. Essentially, what's happening is you set the quantum bits into what's called a superposition, where they're in a weird indeterminate in-between state, where all the outcomes between 0 and 1 are equally likely. And then you're using these matrix operations to transform the internal state space, and then use it to cancel out the bad answers and arrive at the good answer using some probability. And that speed up, as you're using these various techniques and the phase encoding talked about here, um, it's not like a traditional parallel computation, but there could be an analog. And these diagrams try to draw an analog between fork and join that you may be familiar from distributed computing. And the graphs show, where exactly the multiple processing information is happening and how it reduces down into a single answer. And this is a similar way of comparing the initial parallelism efficiency with the destructive interference efficiency, right? In the beginning, one is higher and the other one's lower. And then as you process through the algorithm, it actually flips the other way around. So this is pretty interesting and dangerous stuff, right? Because it provides a credible threat to the systems we use today. But there are a couple reasons why the sky's not falling yet. Quantum computers are pretty delicate, they're complex, they're expensive. Nowadays, a lot of techniques use superconductive materials. You have to cool those down. So you've got these giant cryogenic chambers that are cooling down these chips. These things are expensive to operate, and it's going to be a long time before they're sitting on everybody's desk or that they're widely accessible. This is still largely the domain of large institutional customers. IBM is a big player in this space. There's a couple of specialized private companies that are doing this. And we also have to assume that governments do this stuff too. A lot of the big quantum computers right now are operated by research labs and universities. Quantum algorithms do a bit of an abstraction trick where they are assuming that the main work function is easily implementable. And in reality, this may not be true. If you want to actually break, let's say, AES, then you actually have to implement real AES as a quantum circuit, and that is far from trivial. That could take a lot of gates. That could take a lot of work to actually do. And ironically, there's a no copying limitation in quantum systems. You're not able to, because you're actually manipulating these real physical things. You can't just spawn more ones into existence. You actually have to set them up from the beginning. You can't copy the information from one to the other. You can, however, set up multiple runs at things when you're initializing, and that's possible, but also expensive and challenging to do. What this actually means is, ironically, quantum computing cannot be parallelized using the understanding of parallelization that we are familiar with now, even though some of these algorithms have facets that are similar to parallelization in them. That being said, even though these quantum computers are difficult to build up to a scale where they become a real threat, the world around us has essentially decided that this future is already coming. You are already seeing standards bodies, you're seeing cyber insurance companies, you're seeing various other parties that have that are stakeholders in this space acting like this is only a matter of time. And because of that reason, we largely shouldn't concern ourselves with looking at real quantum computers and figuring out when they become a threat, because this transition will have to happen.
And real quick, just speaking of a matter of time, uh, I do know that we're more than halfway through our time here. So, Gabor, I think we're probably going to have to jump ahead past through some of this, but I want to make sure everyone knows this is recorded and you will receive the slides. So all of the really great information in the slides will be available to review afterwards. So if we do skip over anything as we continue on, just keep that in mind.
And largely, we don't have to skip because we can actually cover this next section somewhat speedily. And that will actually work out really nicely because it turns out that there exists a class of cryptography that is designed to be resistant to quantum computers. Hard for quantum computers to solve than hard for a classical computer to solve. But given that Shor's algorithm only came out in 1994, all of this math in here is considerably newer. Many of these algorithms only date to the early double O's or even more recent. So this is far from proven technology. It's not like Diffie-Hellman, which has been around from the 70s. NIST, which is an American standard-setting body, has announced a competition of sorts for post-quantum cryptographic algorithms, and they received a bunch of submissions. They whittled that down through a number of different rounds to 4, basically. When they posted this competition, they gave 2 different ways to attack these by reducing them down beyond the regular computing security margin or a quantum margin, and all the attacks reduced on the security margin. So largely, nobody is trying to come up with quantum attack for these things yet. Folks are more than content with using regular attacks to prove weaknesses in these things. These are the ones that NIST ended up selecting. You may have heard some of these names before, or you may have not. In our near future, these are going to be a lot more common. Notice that there's only one key agreement mechanism, and NIST didn't like that either, so they actually had to open the contest back up and try to pick an extra one. And that's exactly what ended up happening. They picked HQC as another key agreement mechanism to replace something like Diffie-Hellman. And work has, they've actually standardized many of these as publications, and there will be that future one for HQC coming in a new standard. You can download these, you can read these. And if you do, you will find that there's not a lot of detail inside of them on why things are being done one way or the other. And I think it's natural to be a bit skeptical about these things. A couple of years back, NIST actually snuck in, with help of an NSA, a backdoor random number generator, which luckily folks caught that and raised awareness about that. It was a big scandal, and there's still lingering distrust in the crypto community about whether you have one arm of the government working against the public about these things. But now that these are standardized, hopefully there will be much more scrutiny on them, and folks will try to attack these. Of course, nothing is drop-in. These things are not going to be one-to-one replacements, and there will be a lot of work to pick them up. They have bigger key sizes, which is going to be difficult to work in protocols. IETF is already looking at what changes. It's got a whole working group looking at what changes need to be made to protocols to make this happen. If you're skeptical about these things, you may think, well, surely there's a way we can combine traditional crypto that's tried and true with these newfangled ones. And yes, that is true. Interestingly, many of the government bodies frown on that idea. They say it's too complex. Big tech seems to like this, but of course, they also control a lot of the deployments, so it's much easier for them to iterate. Lots of things to think through, though. And then you also have situations like this. This is an excerpt out of one of these algorithms where you can sign using a bunch of different hash functions, but like, what if one of them breaks? Like, what do? Do you have to like look inside the signature and like see, like, do you have to open the package and look what's inside and reject those? I don't know. Some of these things seem pretty poorly thought out. And SSH is basically abandonware at this point, which is also troubling because that's what we use to talk to many of our machines. So there's a couple gaps with this still happening. So now that you know that this has to happen, what do you do now? You may think it's just like Y2K, where the public thinks that uh, nothing happened, then everything was fine. But if you're in the industry, you know that that was not what happened at all. There was a lot of work that went into retrofitting systems to not break when the time came, and the same thing will have to be done. If you walk away with nothing else from this talk besides what is on this slide, then this talk will have achieved its purpose. This excerpt, and you don't have to read the text, but this is actually from the IETF. These are the folks who work in industry. They develop RFCs for specifications for industry, and they clearly come out and say that agility is recommended. You will need to evaluate agility and assess what you're going to do to implement PQC, develop that migration plan, and also maintain a cryptographic inventory. These are things you absolutely have to do a good job with this transition. And we'll get to why, in many cases, you're probably already doing that. Agility will be necessary, and it cannot be the exceptional case because some of these algorithms are going to fall. And you may have to operate in jurisdictions that have their own pet algorithms. We are moving away from the future where the 50-year-old algorithms are doing all of the work for us and moving into a world where some of these things are going to come out and fall quickly and have to be replaced by something else. And that future will be in some ways very similar to the future that we're living in now with regard to vulnerability and the attacks we're facing from AI trying to break into your systems. What can you do now? These are actionable next steps that you can do today. You can start on building an inventory of what is using cryptography and catalog your risks. If it is broken, what will you do? If you are forced to move, what will you do? You have to understand the blast radius of what is going to be affected if your cryptography is compromised. You can, in many ways, treat it just like any other security vulnerability. You can apply lessons from that space in this space. You need to sequence this work and make time for known migrations. You're not going to be able to do this alone. You likely will have to coordinate with other folks at your institutions. And you will see in the next couple slides that there will be a lot of coordination required for this. And build bridges between security and compliance, because the work that those subject matter experts are doing in their area is very similar to the work that we will have to do with regard to this topic. And as you're doing that, continue to apply pressure on your suppliers. We are all reliant on, in some cases, external dependencies. And those, if they're not ready, then you're sitting around not being able to make a move. So we have to continue to apply pressure on those suppliers. In many ways, the world in front of you is a blank canvas. Just like many of our systems were on a day not too far in the past. That wasn't a very good example of a situation where our reliance on certain solutions created a problem with a very large blast radius. Lots of different institutions were affected all at the same time. That is a risk that we accepted for various reasons. In some cases, not a lot of market power. In many ways, this field is going to be similar. We have to make some difficult decisions about what level of risk we are willing to accept with the solutions that we are reliant on. Very important to understand the impact. What will you do when it happens? The icon is from Heartbleed. That was a software vulnerability that was leaking bits of private keys all over the internet to other parties, and it was an absolute disaster. That was probably the largest example of a time when folks had to reissue, revoke and reissue a large number of keys. Imagine that a compromise of this sort would have the same and bigger impact. You would lose any ability to tell one subject apart from another, legitimate clients away from illegitimate, or simply tell two people apart. You absolutely need a recipe book on what you're going to do if that happens. And consequently, you will also need a process to try to make sure that doesn't happen, because you may be able to switch out some of those vulnerable things ahead of time. This will absolutely be a collaborative effort. You will have to work across your organization to to design for this future where cryptographic agility is important. And to achieve that, you will have to achieve these preconditions, which is the inventory of where it is used and the risks, and have this backed up by policy controls. The technical implementation is really only incidental. It is the policy controls made real using technology. So these ideas are not new. Various adjacent fields have up-leveled to this level. Security and cybersecurity has done this. Identity governance is looking at identity using a very similar sort of understanding. And likely we will need to do a similar up-leveling to our little corner of the industry if we want to better position ourselves for this transition. And this, is just recapping that this really rhymes all over, right? So the exact lessons that one is able to apply for software inventory, vulnerability remediation, incident response, planning for disasters, hurricanes, tornadoes, those sorts of things. There are folks at your institutions that are approaching problems from this point of view today. They might not be looking at it from the perspective of identity and access. They might be focused on a different nameplate, but they are engaged in the same process maturity and having those run books, having those policies and responsibilities laid out, and operationalization. You may, in this community, there is a assertion you can make on the wire called certify. It says that if this party is compromised, it'll notify all the affected parties that have consumed from this identity. And to put that into practice, there's a yearly recurring exercise that this community puts together to put that to build that familiarity with what you actually do in an operationalized setting, so that folks do have practice with what to do. I strongly recommend that you consider how you would rehearse for this kind of situation before it is time to actually react to it in earnest. This leaves our community with some challenging questions. When so much of how you react to a post-quantum cryptographically agile world is dependent on your local circumstances at your institution, that does make it much more difficult to share information about what's working and what's not working, because one lesson may not directly translate to the circumstances of someone else. Our community will ultimately have to wrestle with those questions and how we can better share information when in the past we had common technology, we had and we were talking a lot about having policy commonalities, right? If there are fewer commonalities, we may need to change how we offer value in our community so that we continue to be an effective advocate for each other. The Cryptographic Agility Working Group, Evolution Working Group, we are on that working group. This community specifically spun up this working group to look at this problem, to develop some specific next steps, and act as a knowledge sharing body. That is why we're giving this presentation. We really appreciate this opportunity. This working group is doing a fair amount of work and delivering a number of deliverables. We are currently looking at, we're currently at the questionnaire for software authors that seeks to evaluate those products' cryptographic agility, their ability to move to an agile world, and understand the specific risks and blast radius of the compromise. And we will process the results of that questionnaire to arrive at our remaining deliverables. We also do advocacy work. We're doing talks like this. We're working with other working groups also to spread awareness that lots of work remains, and that folks all across the community and their own institutions will have to do part of this work to bring the future that we want into being. And I repeat the call to action. This slide was actually revealed to you earlier, but here it is again. These are actionable next steps you can do. You can start building an inventory of existing processes that use cryptography and understand what will happen if it is broken or if you're forced to move. Do understand that blast radius, because everything depends on those. Sequence this work together with other initiatives that you have going on and other priorities at your institution to make sure that time is allowed for this while you can still do it before it becomes an emergency. And collaborate between your security and compliance folks, because they understand this language that we need to learn to speak also. They understand that up-leveled process maturity that looks at things from a governance standpoint, from an inventory standpoint, and a risk standpoint. That framing is one we can benefit from as we have to learn how to thrive in this world. And
yeah, we have arrived
questions.
at time for any questions or answers. I know that Mark Rank submitted a question in the Q&A function. I believe, and someone can correct me if I'm wrong, I believe the typed answer should be visible to everyone. Rob went ahead and typed a response to Mark's question, which was, what practical steps should organizations be considering to manage the risks of increasing capabilities of nation states to perform quantum attacks against existing cryptographic systems? And again, and I believe anyone can read the response that Rob typed out, but in general, it comes down to preparation and recognizing, like, all of this, recognizing that this, while it is a real threat, it is a real scenario that we're having to deal with. It's not, again, the sky is not falling. You don't have to rush. You don't have because rushing, you're going to make a mistake. Right. Like, there are very smart people working on this. There are very smart people. We've got a community of practice. The Cryptographic Evolution Working Group is working on this, largely focused on Internet 2 and InCommon services, but we are doing this for the good of the community, so that the output of these the output of the working group can be shared and be used at your own institutions. The surveys that we develop, you should be able to leverage those in your own way moving forward in the future. Rob, did you want to speak to anything in particular?
Well, I mean, I will add sort of to what you said. It's not so much the sky is falling as it is maybe that there's this meteor out there, and we know it's headed this way, and we can do some math and figure out that it's probably going to hit us with maybe a 70% chance of hitting us in 40 years and maybe a 3% chance of hitting us in 5 years, but we don't really know for sure. But the reality is the sky isn't falling yet. But if we don't do something now to prepare for what we'll do if we find out that those predictions are going to become reality, then we'll find ourselves in a situation where we need to do something faster than we can actually do it. So the key now, I think, is to realize that we're probably going to have to do something fairly expensive sometime in the medium term. And if we can prepare ourselves for doing it now, then when the time comes to actually do it, it'll be a whole lot less painful for us. Imagine if everyone who had potential user information lost in the Canvas experience had already anticipated that, oh yeah, Canvas is probably going to get hacked this way sometime in the future. And when it does, here's what we're going to do. It would have been a whole lot easier for all of us if we had sort of, predicted that. Well, this is one of those cases where we can predict that something similar to that is going to happen. We just don't know when. Let's go ahead and prepare ourselves for it, since we know that it might well be coming. It's a it's a bit of a luxury that we have in a sense. We know that this stuff is happening. I don't think we really had the luxury of guessing that Canvas was going to get hacked, and maybe we could have. 2020 hindsight, I suppose.
So I believe we have just a few more minutes. If anyone else has any questions, I don't see that any have been submitted in the Q&A function. But if anyone wants us to answer anything in particular, you can just put it in chat if you'd like. Otherwise, I think we're just about at where Jody will pull us all off stage and take us to the finish here.
Yeah, I love getting my virtual hook out to yoink everyone off stage. No, this was an amazing conversation. Thank you, Gabor and Rob and Grady, for